So like Justin talked about, what I'm going to be talking about is the research that I do, which is in this subfield called Galactic Archaeology. And unlike some of the James Webb images that Justin was showing, we're not really looking at stuff very far away. We're trying to understand things more locally and understand really the history of our own galaxy, the Milky Way. And the reason that we call it galactic archaeology is kind of a fun a fun little way to like relate to what the field is doing. Basically, like archaeology, we're trying to study the history of something. In this case, the Milky Way galaxy. And really, the analogy we're trying to make between the archaeologist, so you might have kind of this cartoonish image of the archaeologist in your mind, and the astronomer is kind of this following like set of logic. So, like the archaeologist, we're trying to essentially look at fossils of the thing that we're trying to study. So archaeologists might be trying to study what the Earth looked like in the past through its fossil records, like bones of the dinosaurs, for example. But for the astronomer, the galactic archaeologist, really the fossils that we're looking at are the stars within our own galaxy and how we can use these to study the past. The various tools that we use to do this are really numerous. So in order to be able to do our studies, really need spectroscopy, photometry, and astrometry to be able to do these types of studies. And I'll go into like kind of what all those are a little bit later. And then finally, kind of the record or the things that we're trying to understand about the stars are their chemistry, their kinematics, and their age. And really how these three different parameters all end up relating to what is going on in our galaxy at a given time. So I think really for the first part of this little talk here, I'm going to try to go into like what chemistry, kinematics, and age is in this context, and why it's important for understanding kind of the overall structure of the Milky Way. So I think the first most important one to go into is chemistry. So kind of like what Justin was showing about looking at those chemical lines of those very distant galaxies. Even in the Milky Way, understanding the chemistry of their stars is really important for understanding what it might have looked like in the past. So just kind of like a reminder of what chemistry is basically we're looking at elements of something. And in this case, we're looking at the elements that are present in the atmosphere of a star. And usually we measure these relative to the amount of elements that you would find in our sun. And how we usually get these measurements are from spectroscopy. So just like Justin was showing, this is essentially looking at the amount of light or flux from a star divided out by wavelength and looking at how that amount of light changes over time. And really, the thing that we're trying to measure from all this is something that I'm going to say a lot throughout this talk, which is called metallicity, which is really just the ratio between iron and hydrogen in the atmosphere of the star that we're looking at. All right. And basically, how we can see how this works when looking at a spectra is like shown on this plot here on the right. So all these different squiggly lines here are the spectra for a star that is the same size and the same temperature. But as you can see, all of these lines don't end up looking exactly the same. And that's because the chemistry of this star is actually different, even though the mass and the temperature is the same for all of them. And so really what we're looking at the top of these lines up here are high metallicity stars, and we're going down to lower metallicity stars at the bottom here. And as you can see, there are certain lines that kind of show up as we move to these different metallicities right here. And it's these types of lines that astronomers end up using in order to measure the chemical content of the star and give some kind of measurement for what the metallicity of that star ends up being. So this is kind of just what metallicity is. But really what's more important for this is what this chemistry means in a galactic context, all right? So really what we're going to be mostly interested in is how does this chemistry or metallicity relate to, say, a star's position in our galaxy? So what we're showing here on the left is an image kind of edge on of our Milky Way galaxy. And what I have labeled here is essentially a bunch of different populations that we know to exist within the Milky Way. So if we consider kind of this to be the midplane of our galaxy, In the center of our galaxy, we have a bar and a bulge. So I'll show this a bit later, but there's kind of a bar-shaped region, and then there's like a spherical bulge of stars that live at the very center of our galaxy. Then we also have the thin disk. So this is pretty much just all the stars that lie right along this midplane right here, make up what we call the thin disk of our galaxy. Then we have the thick disk, which is very creatively named because it's just a slightly thicker disk where there's just, again, more stars kind of centered around the midplane, but there's more of them slightly above and slightly below it than in the thin disk. And then the final thing that we're interested in is something called the halo. And this is pretty much all of the other stars. So there's really, in this image, there are stars like all the way up here, all the way down here, and kind of all around the disk of our galaxy. And these all make up what we call the halo, essentially. And when I'm talking about the positions of all these stars in these different populations in the galaxy, mostly I'm going to be talking about stars and what they look like in the R direction. So this is kind of like the radial direction from the center out, and the Z direction, which is pretty much from the center up, all right? Is kind of what we're looking at. And what's really interesting is if we look at a plot of stars, where they're located in Z and where they're located in R, where this bottom left corner here is going to the center of our galaxy, and we color code all those stars by their metallicity, we see that there's a really strong connection between the population of stars that we're looking at and the metallicity of those stars. Where if we go, essentially from the thin disk at the bottom to the thick disk and up to the halo, we're going from higher metallicity stars up to lower metallicity stars up in the halo, all right? So this is really showing that there's some connection between where a star lives in the galaxy and what it's made of. Another interesting thing to focus on, which is going to be kind of important for later, is thinking about maybe just one of these populations of stars.
Can you explain what that was for them?
Oh, is there a question?
Oh, I was just saying for the general audience, could you explain the colors on that plot?
Yes, in this one, yeah. So this is color coded by the metallicity. So again, this is the ratio of iron to hydrogen. And pretty much the red colors down here means they have a lot more iron in their atmosphere for the star. And if it's bluer, they have a lot less iron. So this is what the red stars are what we would call more metal rich or high metallicity. And the blue stars are metal poor or lower metallicity, essentially. Yeah. Any other questions about this? Sorry, I know it's hard. I can't see anyone there.
No, we're good.
Okay, cool. Yeah, so moving away from just all of the populations all at once, let's now focus on just one of the populations in the galaxy, which is the thin disk. So again, kind of all the stars that just lie right on the central plane right here. And what's interesting is if we look at their metallicity as a function of how far they are from the center of the galaxy, R, we see an interesting trend. We see that as you go from the inner galaxy to the outer galaxy in the thin disk, you again go from higher metallicity or more metal-rich stars to lower metallicity or more metal-poor stars, right? So again, there's some kind of connection going on right here between a star's position in the galaxy and what that star is actually physically made of, right? And this ends up being like really important for understanding not just what the galaxy looks like right now, but what the actual history of our galaxy was. And so it really just comes down to trying to think about why these populations might have different metallicities, why they might be made of different things. And the real answer comes down to this is really due to star formation and how star formation works. So to give like a little background on like the life cycle of a star and kind of how it contributes to its surroundings, what usually happens during a star's lifetime is as it evolves over times, it produces different elements within its atmosphere. And what it does is it starts out with just hydrogen and helium, which is kind of like what our sun's like right now. But over time, it builds up heavier and heavier and heavier elements all the way up to iron, right? So it'll start creating, through these fusion processes, more and more elements within its atmosphere. Then, when the star dies, it explodes and actually releases all those heavy metals back into space. And then what's amazing about this kind of life cycle is new stars are then born in the gas from those stars that just died and exploded. So that means that these new stars are born in gas that has slightly more metals than those first stars that were born had. So this just means that over time, stars get more and more metal rich, and they increase their metallicity over time. So a good way to think about this is that just like over time, you would expect that older stars would be more metal poor, and younger stars would generally be more metal rich, right? So because of this, this really tells us of something about the star formation of our galaxy, and which populations were born first and which populations were born last. So the real simple one is because the halo is more metal poor than the thick disk, and the thick disk is more metal poor than the thin disk, this tells us that the halo in our galaxy was the thing to be formed first, then the thick disk, and then finally the thin disk. So this kind of tells us a little bit about the history of our Milky Way and how things were created over time. Another interesting thing about, going back one, about why we see this metallicity gradient in the thin disk, so high metallicity in the center and low metallicity on the outside, is this actually implies that the thin disk formed from the inside out. So the inside part formed first, and then it slowly kind of formed farther and farther out over time. So that's kind of shown through the schematic here, where basically you have gas kind of falling onto the center of our galaxy. And because it formed first in the center, that means that the central stars had more time to get to higher and higher metallicities, and that as the gas poured in farther and farther out, these don't have as much time to form higher and higher metallicity stars. That's why they appear to be lower metallicity than the inside of the galaxy overall. So this really shows like how powerful just understanding what stars are made of can tell us a lot about what the history of our overall galaxy looks like. So while this is the chemistry of these stars, the next thing that we're going to be interested in is the kinematics of the stars. So this kinematics is just basically how a star ends up moving around our galaxy over time. All right, and how astronomers measure this, I'm going to mention this very briefly for the technically minded people that are interested in this. But basically how we measure the velocity of stars is we take their total motion in 3D space and we break it down into just 3 directions, essentially. So we usually measure the star's velocity towards the galactic center, in the direction of the galactic rotation, and kind of up and down, in and out of the plane of the galaxy, right? So that's kind of the technical description. But I think a better way to illustrate what the orbits of stars look like in these different populations are through a couple of videos that I made. So if we first focus on a star in the disk, so remember the stars in the disk are ones that kind of just stay in the midplane of our galaxy for the most part, which I've shown by kind of like this blue circle right here. And when a star is in the disk, and it ends up moving around our galaxy over time, it pretty much mostly moves in kind of an oval shape and kind of oscillates a little bit up and down, but always kind of stays close to the disk throughout its entire time. So all these disk stars like really stay in close and kind of oscillate around as they're moving around the galaxy over billions of years. And this is kind of what its like total orbit looks like. The halo, on the other hand, looks nothing like the disk stars. So a halo star is going to only be visiting kind of the midplane of our galaxy every so often. But really what it's going to be doing over time is going on these big, wild, crazy orbits around our galaxy in kind of like in a very kind of random fashion over its long period of time. So again, these kinematics look very, very different from what the disk looks like because they're so much more chaotic than what's happening in the disk of our galaxy. So again, this is kind of just showing how chaotic this whole motion of a halo star is. And again, what's not surprising at this point, but what's interesting about these kinematics is if we know that, for instance, the disk stars kind of live in this part of our velocity diagram, and the halo is all the way up here, then just like what I talked about before, all of these kind of velocities of the stars are related to what the stars are made of. So this is kind of shown in the bottom right plot right here, where again, if we're going from the disk stars that are down in this like bottom right corner up to the halo in the top left, again, we're going kind of from higher metallicity stars up to those lower metallicity stars that live in this part of the diagram up here. So again, this is kind of just showing that there's some connection between what a star is made of, where it's located in our galaxy, and how it actually moves around our galaxy. All these things are kind of intertwined, which is really amazing. But again, let's now focus not on all the populations in the galaxy, like we were showing on that last plot, but let's see what the motions of the stars look like just in the thin disk of our galaxy. So again, what the motions of all the stars look like just in the central plane of our galaxy. And that's shown in this plot here on the left. So again, the axes are not too important to focus on this for the moment. But I think the important thing to notice about this plot is that there's a lot of clumps and arches in this plot. So it seems that in the thin disk, there are certain stars that prefer to be moving in similar ways as other types of stars. And they all end up kind of clumping together in this velocity diagram. And you might wonder maybe, why is this happening, or what is going on, or why would some stars prefer to be moving in certain kinds of ways with one another? And the answer ends up actually being just very simply that this is a result of our galaxy having spiral arms in it, which I'll show in a second. But through simulations, we've been able to show that when you put spiral arms into a galaxy, you expect all these stars to kind of clump up together in kinematic space. So what's really important about this for the thin disk is this means that these kinematics, these velocities of these stars in the disk, can tell us something about what the spiral arms in our galaxy actually look like and how they might have changed over time, essentially. All right. So again,
we've got a question real quick.
Yes, absolutely, please.
So is the clumping a resonance effect? Is what you're saying?
Yes, that is exactly right. Yeah. So this is a resonance effect. So basically, because the spiral arms will move at a certain speed, for example, some stars are more likely to want to be moving at the speed of those spiral arms. So this is like resonances. And you end up getting clumps of those stars along the resonances with the spiral arms.
And the spiral arms themselves are resonance features too, correct?
Yes, yeah, they are resonance features, and they may not be, we'll get into this a bit, but they may not be constant resonant features, which makes this picture a bit more complicated. But yeah, they are resonant features in the galaxy.
Thank you.
Yeah, no problem. Oops, sorry, skipping ahead. So yes, so this is kind of like, again, what the kinematics of the stars look like in our galaxy. And again, the important thing just kind of to take away from this is they connect to the chemistry, they connect to the position of things in our galaxy, and they connect to these resonance features that we just talked about, like spiral arms. So again, if we start building all these things together, we can start piecing together what our galaxy might look like as a whole. The last thing to focus on that I brought up is ages of stars. And the reason that this is important is because really what we want to do in the end of our whole analysis is reconstruct the exact history of our galaxy. And the only way to know how long ago something happened is if we actually know how old the stars are that we're looking at that might have caused something that we're seeing in the galaxy. There's lots of different ways to determine the ages for individual stars. I've kind of just listed them here on the screen. I'm not going to go into depth. Someone can ask about what they are a bit later if they're curious. I think just the takeaway that I'm going to say for this is that it's actually very, very, very difficult to figure out what the age of a star is. And usually we're not able to actually know what the age of an individual star is when doing galactic archaeology. So this ends up really kind of complicating things for us. But one kind of cool thing that ends up happening, and one interesting effect that we end up seeing, is kind of shown on these plots here. So in each of these plots, we're essentially looking at the three components of velocity for groups of stars where we know the age of the star, where we're actually able to figure out what the ages of these stars are. And what's very interesting is if you look at older and older groups of stars, you see that this scatter around 0 grows and grows and grows over time. So this scatter is what we call velocity dispersion. So pretty much it's just how close or far away all the stars are from being at 0 velocity for that group of stars. So this is what's going to be very interesting about this, is this shows that if we were to look at the scatter and velocity, or the velocity dispersion for a group of stars, it's directly related to what the age of that group of stars are. So if you look at a group of stars and they have a very small velocity scatter, that probably means that you're looking at a very young group of stars. If it has a very large velocity scatter, on the other hand, that means you're again looking at a much older group of stars. So again, this is kind of tying everything together, like I've been saying this whole time, where there's this really interconnection going on between the age of the stars and the kinematics of the stars that, again, is going to be very important and helpful for us to be able to reconstruct the history of our Milky Way galaxy. So these are kind of the three parameters that we have to think about when doing galactic archaeology. But now some people might wonder, where does all the data come from to make all these plots and to actually do our analysis? And that's actually what I find to be the coolest part, and what I wanted to go into a little bit. So the first thing to think about where the data comes from is maybe to think about how do we figure out where the position and velocities are of stars in our galaxy? And the position and the velocity of stars come from my favorite astronomy mission, which is called Gaia. So Gaia is a satellite that I'm going to show a video of in a second, that was built and is run by the European Space Agency. And Gaia has been going on for almost a decade, I think, amount of time. But the really impressive thing is Gaia has been able to observe 1.8 billion stars. Yes, billion with a B, within our galaxy. And they're able to get the positions and the velocities and a lot of other data on all of these stars. So that's why I think it's my favorite thing that's ever happened in astronomy, because it's been so revolutionary for stellar astronomy, because we have just so much information now on such a large number of stars in our galaxy that we just didn't have 10 years ago. And to kind of give a little explanation of what Gaia is, I have a little video here that I wanted to go through that shows actually how Gaia works. Can I control the video? Sorry, one sec. Come on. There we go. Yes, so what we're looking at right here is the Gaia spacecraft. So in the Gaia spacecraft, it actually has 2 mirrors, and it observes 2 parts of the sky at the exact same time. So it's about to show that right here, where you see that it has its 2 beams of light, where it actually looks at 2 different places in space at the exact same time. And what happens is both of these kind of images of the stars go into the satellite, and they end up getting bounced down onto the instrument panel here. Right, so this is kind of where all the data ends up being taken in Gaia, is on this panel right here. And here's the second one that goes down at the same time, essentially. And as it's, oops, come on. Yeah. And as it spins around over time, essentially all these stars end up streaking out over at the instrument panel over time. And what happens is, as it goes over each of these little CCDs right here, is it actually records the position of the star, takes a couple spectra also of the star, and then it sends all the data back to Earth. And it's doing this not just for one star, but for every single star that passes over its field of view. And it's only by like knowing the positions of all these stars in the sky that it's able to figure out, as you take multiple positions year after year after year, what the distance to these stars are and what their actual motion is through our galaxy. And a cool visualization of the entire Gaia data set is shown in this image right here. So this is like my favorite image in all of astronomy. And essentially what we're looking at here is all 1.8 billion stars in Gaia, kind of color-coded by their distance and their color, but mostly by their distance. So this allows us to actually get a view of what our galaxy looks like from the inside out. You're actually able to see, like I said, the plane of the galaxy, the bulge in the center. You're able to see some of the Magellanic Clouds that are kind of, which are galaxies, which are dwarf galaxies circling our galaxy. So this is like a really, really powerful instrument and survey that we're able to utilize to do these types of analyses. And it's really, really amazing. And one of the most amazing things about Gaia, I think, is that it's completely available to the public. So if anyone was very interested, they could go and download all 1.8 billion lines of data and go look at all of them. So if you're more technically minded and you want to do a little analysis and look at some stuff, if you go to the Gaia archive, which is I have the link shown right here, or you can Google it and you'll find it easily. You're able to very easily search throughout their catalog and pull out all the data and look at it, which is what I do for my research every day. Another really cool thing that they have available, which I wanted to do like a very quick demo of, is something called ESAA Sky, which actually uses data from the Gaia spacecraft to actually visualize what the night sky looks like. So we'll let it up. So it has two different modes. We'll start in Explorer mode right now, which is kind of just giving basic info on something we might be looking at. And it'll pretty much what it'll do is it'll just plop you into a random place in the sky, and you can actually see the stars and things that would be in that part of the galaxy. Also, it's cool in Explorer views. You can just like do a randomizing feature, and it'll take you to a random place on the sky for you to look at. Where you do another random thing. We're looking at another kind of galaxy field. What's also cool is if you go into science mode, and if we like zoom in like a portion of the sky, like this, that I think we want to do. What you're actually able to do is actually look at real life data from an astronomy catalog. So if you click on one of these catalogs, for example, and like go to some pointing on the sky, when it'll load eventually. It'll actually give you data on that particular star that you can click in, go download, and do whatever you want with. So again, this is a really cool tool for people that want to like get their hands dirty a little bit, but also maybe just have fun and look around the night sky and find some interesting, cool images that you would have never seen before. So they do both that. It's a pretty awesome tool. I suggest checking it out. So that's everything that I kind of have for Gaia. The other amount of data that I look at also has to do with understanding the chemistry of stars. So as we talked about in the very beginning, usually people would do this with spectroscopy. So again, kind of breaking up the wavelengths of light and getting the flux or the amount of light at each of these different wavelengths. But as we like to say a little bit in astronomy, spectroscopy is expensive. It requires more complex instruments, and you need like more light and brighter stars to make this happen. But photometry is cheap. Photometry is much, much easier to get. And that's because how photometry works is instead of breaking down the light from the star in such a fine grid like this, in photometry, for example, you would just count up all the light in, say, like this blue box and the red box, and just get one value for how much light you're seeing for some like very wide wavelength range. So it makes it a kind of a quick and dirty way to study what a star ends up looking like. And these are kind of some of the sources that I get my photometry from. And again, these are all publicly available. There's things that they have websites that you can go check out and download their data. And most of them also have like image portals where you can even look at images of stars in them. They're really cool things. And the reason that I use photometry and why photometry works for looking at the chemistry of stars is kind of shown here on this plot on the right. So here what we're looking at is what we call in stellar astronomy an HR diagram, where essentially we're looking at the color of a star. So this is very much just the difference in value between two photometric bands, and this acts as a proxy for the star's temperature. And on the y-axis here, we're looking at the absolute magnitude of the star. So this is when you combined the photometry from a star and its distance to get a proxy for the star's luminosity. And what's really amazing in this HR diagram is if we now kind of color code all these stars by what their metallicity is, we see that there's this really clear gradient in the HR diagram, again, going from kind of high metallicity to low metallicity. So all this really is to demonstrate is that you don't need fancy spectroscopy to understand the chemistry of stars. You can actually use just photometry in kind of an image just like this to estimate what the metallicity of a star ends up looking like. So that's kind of like where I get all my data. And now let's kind of combine these two things together to figure out what kinematics and chemistry looks like, specifically for the disk in the Milky Way. So my research really focuses on just looking at the thin disk and not all the other populations in the galaxy. So first, we're going to show kind of the same image we showed before, which is of the kinematics, where we see, again, a bunch of kind of clumping in kinematic space. That's due to these resonances with the spiral arms. And now we're also going to show the same kinematic plot, but now everything here is color-coded by metallicity. So here, all the blue data points are the low metallicity or metal-poor objects, and all the red data points are the high metallicity or metal-rich objects. So there's kind of two interesting features that we end up getting from the plot here on the right. So the first one is that on average, you see that on the bottom part of the plot, most of these stars are higher metallicity. And on the top part of the plot, most of these stars are lower metallicity. And again, this is just kind of a remnant of the metallicity gradient that's due to the inside-out formation of the disk of our galaxy. Another interesting thing is that if we look at some of these clumps in kinematic space and relate to them over here, we'll see that there's some weird pockets of either like higher metallicity or lower metallicity objects where we don't really think they should belong there based on just the metallicity gradient of our galaxy. And to kind of give away what this means is basically these pockets of like high and low metallicity are due to interactions with spiral arms, leading to something that we call radial migration. And this just basically means that when a star interacts with a spiral arm, it makes it move to a totally different part of the galaxy that it wouldn't have been in normally if it was just going around in a circle doing kind of its own thing. So again, these kind of little pockets of weird, peculiar metallicity places are really interesting for understanding how stars interact with spiral arms in our galaxy. The one thing I'm conveniently leaving out of all of this is what are the ages of these stars, though. Again, determining the ages of stars is something that's very difficult. But one thing to keep in mind is that, again, remember that velocity scatter increases with age. So this plot here on the left, now everything is color-coded by that velocity scatter, where again, the blue kind of points are the lower velocity scatter, and the red points are the higher velocity scatter. So here, what we're actually really seeing now are pockets of young stars that have low velocity scatter, and pockets of older stars that have much higher velocity scatter. So again, even though we don't directly have age measurements for all these stars, there's still clues from the velocity scatter plot where the young and the old stars are in the data set that I'm using. So again, we can now start to not just reconstruct the general history of our galaxy, but try to start to pinpoint exactly when things started happening in our galaxy's history. And so this kind of brings us to the final point here, where I'm going to put together a few of these points to give some interesting results that we can get from our galactic archaeology experiment. So the first interesting, the interesting thing from the kinematics that we get, again, is they tell us about how stars interacted with the spiral arm and the bar. The chemistry then tells us where in the galaxy these stars were born, most likely. And the age allows us to tell us when they were born. So again, these are all the different things we have to start putting together to go into the kind of the final results I'm going to talk about real quickly right now. The first interesting thing that we learned from this, which I'm talking about just very briefly, I think, is what we learn about the galactic bar. So we can learn about the galactic bar from these resonance structures shown in the white oval here in our kinematics plot. And again, the bar of our galaxy is just kind of this like really bar-like feature in the center of our galaxy. And these resonance features are said to be influenced by the bar in our galaxy. And what's interesting is because we know the chemistry of these stars and we know the ages of these stars, we can actually reconstruct where they were born in our galaxy. And what's cool is if you look at these different kind of resonance features, like this one, and that one, we see that they have actually different birth radii distributions. So birth radius is just where the star was born in the galaxy relative to the galactic center. And as you go to these different resonance features, you have stars that were born in the inner galaxy and slowly born in the outer part of the galaxy. And this ends up actually being evidence of the bar slowing down over time. So it doesn't actually spin at a constant speed, but over time, it's been slowly slowing down. Another thing that we can learn from our data set has to do with actually external influences on our own galaxy. So actually we can start to understand a little bit about what happens when nearby galaxies interact with our galaxy. The answer is basically they change shape and cause some interesting features. So this video I'm going to play right here is going to be a very awesome simulation from a colleague of mine, Jason Hunt, who does a lot of like really amazing simulation works of our Milky Way galaxy. But basically what we're looking at in this top left plot here is like a top-down view of our galaxy. And the top right plot is an edge-on view of our galaxy. And what you're going to see at some point in this video is a green dot pass in front of the field of view on the left here. That's going to be an external galaxy that's actually orbiting our own galaxy over time. And what's really amazing is as this galaxy passes by more and more over time, you see that it actually changes what the shape of our galaxy is. You end up getting these spiral arm features, for example, just from an external galaxy passing us by and disrupting all the stars that are currently in the galaxy. And now it gets really chaotic as this galaxy is getting closer and closer in. And it's really messing things up. What's also really interesting about this interaction that we get with this external galaxy is not only does it make kind of the spiral arms that we showed here in the left, but it actually warps the shape of the disk of our galaxy. So if you look in the top right plot over here, you see that we actually have like these flared edges here and here that are actually warping the shape of the disk of the galaxy. And this warp is really due to all these external influences and these passing by of nearby galaxies relative to ours. And what's really cool is you can actually see evidence of this in the data that I work with. So without going into too much detail about this, essentially we're looking at stars as they increase with age, and we're looking at this parameter B that essentially just says how strong the warp is for those types of stars that we're looking at. Whereas you go up on the y-axis, you're pretty much going to a stronger and stronger warp. And what we end up seeing is that the strength of this warp actually increases with age. And we actually see this.
By warp, do you mean a nonlinear like flare, or are you talking about an actual like change of the angular momentum vector for different radii?
It is both.
Okay.
Like it physically manifests in an asymmetry, so almost like a tilting of the disk relative to like the zero axis. And that also then ends up changing the angular momentum of the star's orbits. So it is both of these things. Yeah. And like the really extreme example I'm showing in this red box here, where you see this really big increase in the strength of the warp, is probably actually evidence of a past merger between our galaxy and an external one. So these are two galaxies actually colliding with one another and disrupting the stars so much that we see this really large increase in what we would call the warp in this example. Which is really kind of amazing to see, again, just from looking at stars within our own galaxy. And then the final thing that we might want to think about is what we can learn about the spiral arms in our galaxy. So also in my PhD work, I've been working on my own simulations to study spiral arms. They're not nearly as pretty as Jason Hunt's, as I was showing previously, but they're still very interesting. So the video I'm going to play here on the left is one of my simulations that runs over time, where this top panel is pretty much just the top-down view, and the bottom one is just the edge-on view of this simulated galaxy. And the way that I'm setting up these galaxies is I'm essentially making it so that the spiral arms kind of disappear and reappear over time with kind of some kind of cadence. This is what we call essentially transient spiral arms. And the whole idea behind transient spiral arms is due kind of to these external forces, where if we expect that there's like in a galaxy, for example, orbiting around ours, we would expect kind of these spiral arms to like come and go over time, kind of like what we see here on the simulation on the left. And what's really great about these simulations is you can actually now pull out a group of stars from these simulations, look at their kinematics, which is shown here on the left, and we see that they end up looking pretty similar to what we see in the observations that we were looking at. So again, this is kind of showing that really we maybe can use these observations to try to understand what the spiral arms look like in our galaxy. And kind of just one example of like how we can actually learn something about our spiral arms is shown in these three plots right here. So here we're essentially showing the kinematics for three different simulations. The difference between all of these simulations is pretty much how long the spiral arms last. So on the left panel over here, the spiral arms only last, I know only for about 500 million years. And then they go away and they come back again 500 million years later. On the right, though, we're looking at a simulation where the spiral arms last much longer. They last 2 billion years and then go away and then come back again 2 billion years later. And what's interesting is in each of these plots, we're essentially looking at just stars of all ages, for example. And kind of qualitatively, all of these simulations look very similar to one another. There's not a big difference between each of them. What's really interesting, though, is if we look at these same kinematic plots for these simulations, but just for the young stars. And if we look at just for the young stars, we end up seeing that there's a lot more clumping in kinematic space for these long-lived spiral arms than for these short-lived spiral arms. And again, this is a little bit more similar to what we see in the observations, where we actually see clumping of young stars in kinematic space. So again, this might be telling us that really maybe the spiral arms in our galaxy are fairly long-lived. Yeah, they have a fairly long lifetime. I'm still doing future work on this. This is kind of what the end of my thesis is going to be like. But it's still kind of a cool result to look at. Anyway, so this is kind of all the general results I wanted to bring forward. But really, I think the main takeaways to take away from all of this is just galactic archaeologists are really working to use a really large variety of data to try to study the history of the Milky Way, which ends up being a very difficult thing. And what's really awesome, I think, about this field is that much of this data is very numerous. There's a lot of it, and it's all available to the public. So there's a lot of cool things that people can go look at if they're really interested in to try to understand what the stars in our galaxy look like. And really, when we start combining all this data, there's some interesting things we can learn about the history of our galaxy. We know that it has a bar, that it's slowed down over time, that we've had some major interactions with external galaxies, and that maybe we have proof that our spiral arms are fairly long-lived within our galaxy. So these are all amazing things that we're able to understand by just looking at the stars within our own Milky Way. So again, thank you all so much for like listening to all this. I hope it was interesting. I'm happy to take any questions either right now, or here is also my email up on the slide if anyone wants to email me and ask me any questions later on.
Any questions for Ilija? Yeah, go ahead.
So the boa, if it's slowing down, do we think it will eventually stop? And if that happens, what effects will it have on the galaxy?
I think more the answer is that it won't like stop as a solid structure. It would more like dissipate. Like like just because it will slow down so much that it won't have enough like self-gravitation to like keep stars actually like located in this bar area. As for like what that will mean for our galaxy, usually see a lot of you see a lot of galaxies that don't have like bars or spiral arm features as ones that are kind of old and dead. So this is probably just going to be a much longer period in our galaxy's history, maybe, where there's not much star formation going on. There's not a lot of stars being born, and all the stars are kind of just orbiting around willy-nilly without much structure to them.
Okay. First of all, really interesting stuff. I have too many questions to fit into a reasonable time frame.
And please email me if you want to. Feel free.
So a couple things. Can we go towards the beginning when we we're talking about the thin disk formation?
Oh, the inside-out formation.
Yeah.
Yeah, for sure.
All right. So question: This can't be an accretion formation in that way. It's a cooling effect, right?
So it is kind of an accretion thing.
How could it be? How could it accrete and be so planar? I mean, if new materials coming in at different angular momentums.
It's like a conservation of angular momentum thing. So you end up having.
But you'd expect a much more warped disk at that point.
Well, so it's more of the gas that ends up settling is of some angular momentum that is like more preferentially want to be conserved and collapse into like a disk-like structure. So there's like lots of gas clouds that are still probably orbiting in like very random motions around the galaxy. But it just happens that there was some parts of the gas that aligned with whatever rotation was lining up with like the bulge area, for example, that had a similar angular momentum and that were more preferentially collapsed onto the disk.
Is there enough of a mixing term between gas at different radii that you would expect? I mean, I do accretion disks. Accretion disks are very much smaller to galaxies, so the mixing there is not hard to do. But like on the scale of a galaxy, is there enough gas mixing at different radii for an inside-out forming disk to be so planar?
I mean, I think the answer just has to be yes, because observationally it does work out like that. Right. I mean, some of this early, it is fair to say that some of this very early galaxy formation stuff is still it's something we still don't have like very good models to explain even now. I mean, these are things that happened like 10 billion years ago in the past. It's still like very early in the Milky Way's history. So I still don't think we have the best. We don't have like all the best theory to describe it because of that.
Yeah, because I can understand a lot better is if the overall toroid of the early galaxy already had its angular momentum, and it was just cooling into that disk shape over time, rather than it accreting random gas over time and it happened to form this nice disk.
Yeah, I see where you're coming from, and I think I don't have quite the knowledge for this part. But I think if you're interested in this more and you want to look at this more, there's I know like the most cutting edge simulations that try to do like the early universe simulations of galaxies are called FIRE, like the flame, FIRE. And if you look at like some, like if you want to like look into this, if you look at some papers where they do these simulations in FIRE, they do end up seeing some of this accretion, this flattening of the disk happening in those simulations. So maybe that might be a good place to kind of look to maybe really understand the physics of this a bit better.
Yeah, but
this is, I just didn't want to interrupt you earlier while you were talking. I don't want to ruin your flow, but whenever I'm not able to wrap my head around the fact that you said that the metallicity of a galaxy or the metallicity of the star is ratio between the metal and the gas. But whenever I was looking at it, I didn't understand why are there negative.
Oh, yes. I mean, this is a dumb astronomy thing. So it's two reasons. So one, the metallicity is always relative to the metallicity of the sun, and it's in log space.
So 0 is the sun.
Yeah, so 0 is 1. 0 is a ratio of 1. Yeah, 0 is a ratio of 1, and negative is a ratio less than 1.
Okay.
I'm glad you went there. You're like, that doesn't
Astronomers
make
love
sense.
It's like ratios don't go.
Yeah, I know. But I feel like I'm so used to thinking in log space because so much astronomy is that I forget to mention it sometimes. But
Sometimes it's the logs of logs.
yeah, the logs of logs, all that stuff.
So, as a non-astronomer and as a non-physicist, in fact, as a social scientist, I'm afraid to ask a question, but I'm going to ask it anyway. So I'm intrigued by your discussion of kinematics.
Hmm?
And for me, it raises the question of, is there a fixed point of reference? And if there isn't, how does it complicate our, how do we measure kinematics in regards to what fixed or non-fixed point of reference?
Yes, so that's a very difficult thing. So I mean, so when you get raw data, usually from these telescopes, the reference point that you're looking at is from the sun. So you'd imagine, or from the Earth essentially. So you'd imagine telescope looking up from Earth, and you're looking in the night sky, and all you see is the motion in the plane of the sky, and then the motion in and out of the plane of the sky, which you get from like the Doppler effect thing that Justin mentioned like a while ago. And then in order to like get it into something that's more usable, so like this galactic frame, it's essentially then just math. It's essentially then just like if we know that we were looking at this point in the sky at like this time, we can then kind of like revert the velocities into a different reference point so that they all kind of align better in this galactic reference frame. So the answer, yes, that's pretty much the answer. We always see it from the Earth, and we have to do some math to like kind of reconstruct what it should be in a common point.
Reference point, the Earth, the sun is also moving.
Sorry,
We know how fast the sun is rotating. So
Yeah.
He was just talking about the complication of the fact that the sun is moving.
yeah, I mean, yeah, there's also the sun's motion is built into this as well, which we don't know very well, which is also something we don't know 100%. We think we know the motion of the sun through the galaxy, but we're not totally sure about that. So that's another complication.
I have a quick question, and then we might wrap it up. But a quick, you reminded me, it really mentioned that you can download the entire catalog of Gaia onto your computer if you wanted to. But
Yes.
Astronomers who work on this data also have to do that. So back before I defended, when I was at grad school in the same department as Ilija, when that data came out, our department, this was before the dark time, before COVID. So the department was really busy, buzzing around, and usually if you would go in at any time, you would see a group of people talking, you would have people in their cubicles, you have professors in offices. The day that Gaia was released for the first time to the public, we went in and it was crickets. But that's because more than half the department all went to their computers and downloaded it at the same time. So it looked like everybody just disappeared. But Ilija, can you go to towards the end of your talk where you have the plot of age as a function of was it distance out of the disk versus age?
Or was this velocity scatter? This one?
No, keep it toward the end of your talk.
I'm gonna get out of full screen. So this one?
You're saying that the warp? Yeah. Okay.
Yes. Yeah.
Okay. So there's a new class that I'm teaching called Extragalactic Astronomy, and throughout, like even just a couple of weeks in, we've already made the joke of for studying other galaxies, they're farther away, they're harder to measure, they're harder to study. So with the kinds of numbers that we report, if you're within a factor of 10, you basically have the right answer. It doesn't really matter what the little itty bitty numbers. It's just, is it 10 to the 10? Is it 10 to the 9? That's all you really need to know. Ilija, I might be missing something, but that looks like an extragalactic error bar, sir.
Oh, no, it's,
That's huge. What is? what's
I
going
said
on?
it could be. Also,
Oh, I see.
also to be perfectly fair, I am not the only one to have noticed this, and other people in their data sets have noticed this at a much higher degree of statistical significance. So I think it's just it has to do more with my data set and how I'm doing the data analysis. That it's not, I do not get a statistically significant results. But this is a thing that is in other people's data sets, and it is definitely there. It's a real signal.
Not the worst error bar I've ever seen. I mean, you can land planes on some of the error bars.
Oh, I know. So we can have big error bars too.
All right. Last question. Okay, go ahead.
So when you had the simulations of the galaxy streams, the disturber galaxies creating spirals, are those simulations planar? Or are they simulating like axis tilted orbits of those disturbing?
Yeah, no, so when it's the galaxy starts, it's planar. I think the density increases.
Yeah, I meant the disturber galaxy. The disturber galaxy is motion planar here, or is it moving all sorts of different?
I don't know actually enough about the specifics of how it's initially moving.
I was wondering how, like say you put a huge tilt angle on it, like how that would affect the spiral arm formation versus a planar. You'd expect a random incoming angle for a orbiting galaxy.
Yeah, no, that is true. And to be fair, I don't know enough about specifics about the simulation, about what Jason was doing with that part. But the paper is down here. It's his from 2021.
If it's the like first attempt, it might have just started planar, and then like next time we'll add on.
Yeah, I'm sure knowing him, I'm sure this is one example of many simulations that he ran, and he didn't do it just one way.
Well, thank you very much, Ilija. Let's give him one more round of applause. The Chile Troy quad. We'll set up our telescopes and try and catch that green comet. I'm pretty sure the moon is up too, so we'll be looking at some cool things. So grab some last of your pizza, grab some soda, and then we'll slowly migrate up there.
Thanks, Justin.
Yeah, I've been building up all week because I remember how years ago things were, how we're going like better. So, but
Well, I cannot hear you because the background noise. I can't.
Where's the mic? You hear me now?
Mama, you want me to grab your plate?
No, I think because I'm just hearing the chatter. The chatter.
Oh, mic's over there.
Yeah.
I was saying, when you open your Gaia data, are you using the top hat?
You still have on your Star Wars shirt?
Sorry, I can't hear because people talk.
Show Dr.
Yeah.
It gets really useful for that, for like just seeing something really quickly and being able to like section off something and do it like for actual scientific stuff. It's just splitting it up into reading the files and then right now, yeah. We're fine. We're waiting for the room to clear. Can you hear me, Ilija?
I can hear you.
Because I'll bet you.
Now there's less people.
Those who did participate.
So he was asking, he was asking if you use TopCat for analyzing the guy, you know, if you use. So it's a huge data set.
No, I know a lot of people use TopCat. Even people in my research group use TopCat. But I am full coding. I'm full Python. I do everything in code. I don't use a GUI. That's just my preference. But you can. TopCat's a very cool tool to access Gaia because you can download the data like directly from TopCat. They have like a table access protocol to do.
Okay. Yeah, we're toward. It's so easy format. Okay. Yeah.
Yeah, and then another cool thing, if you want to upgrade, if you're interested, There's something called glue viz. It's like glue visualization. And it's like it's a slightly more modern version in TopCat that's like has a backend in Python. So I don't know if you want to get more technically savvy with things. Glue viz is very cool.
Yeah, I do Python, or no, I've done projects with students before with Gaia, working with another professor, and they use a lot of that. That's like what everybody's using.
Yeah, no, I think for students especially, like intro students, like that makes a lot of sense for accessing Gaia.
How far did you have to drive down now?
Good.
Okay, I just wanted to ask you if you stick to the road station.
Wait, sorry, one more time.
So are you?
The microphones are.
It's project.
Yeah.
Yeah, he's got to like really give
I
it.
just wanted to ask you if you speak server operation because your name is South Slaughter.
I can't say that.
Serbo-Croatian, is that what you said?
Server
Yeah,
operation.
you speak Serbo-Croatian because he was recognizing your.
I kind of thought I was from that, but I was like, this is an astronomy question that he's asking. I do not. My dad never taught me. There was a battle in my house. My mom's Greek, my dad's Serbian, and there was a battle in the house of which language to speak.
Well, then maybe you can answer.
And they decided to stop English just to avoid any
That's the
conflict.
language I was wondering. And your name
No
is
higher than
South
15
Slaughter.
meters.
Yeah.
There's no way.
Also, at the beginning of your talk, you conflate archaeology with paleontology.
where you live.
All right, but then how do I make a complaint?
You look at.
Yeah, so speak to you, then yes, talk, and then.
At the beginning of your talk, you conflate archaeology and paleontology.
Oh, yeah. Sorry, I can hear that better. Yes. Okay. Yeah, I could.
No, that's, yeah.
I just thought that was funny.
This was a pilot hot dog.
It's just for here.
Right, it was a little bit talking about paleontology.
When they want to fly back closer to the ground, let them do whatever.
Well, we do,
Yes, goodbye.
so we work, follow.
Yeah, no, you're good.
We have a question for you to ask the hanging down things.
Yeah, you gotta like talk like to the voice of God. Oh,
We're allowed to be done.
And the cameras actually.
That's true.
So like, in some sense, we should.
Why?
Okay, so that's.
Probably just,
It was disturbing livestock.
You have to look this way, but you see us, we have to look that way.
Yeah.
Well, I can actually hear you a lot better if you're facing like the camera.
Yeah, well, it's because
The cameras in the back.
the microphones are like these little hanging orbs
Oh.
right here.
Okay, I couldn't tell from the perspective. They seem like they were farther forward.
No, yeah, no, the microphones are back here, which is why when we're standing up there, we're trying to talk to the screen, you can't hear us because the microphones are back here.
Yeah.
People are asking.
What is the vibration? I mean, I felt the road.
See that in person.
So with the age of the spiral arms,
Yeah.
it does make a lot more sense that they would be at least giga years, because 500 million years is like what, a handful of galactic orbits?
If that.
Yeah. I know, right?
Yeah, but I think that like that theory was going out pretty fast. Like this was like a thing that was floating around
Yeah, I know.
like a few decades ago. That they
I'm
would
gonna
be-
say sus stuff in the mic.
But like I think that's been going out of fashion pretty quickly. Because I agree, I don't think it makes very much sense that
Yeah.
like they lost two orbits and
Right,
dissipated.
exactly.
Yeah, it does seem wild. But there's still debate about how
Right.
point that down.
Sure, yeah.
So another thing with Gaia data, what's the shadow of the galactic core? Like how far can we, how close in can we see angular? I mean, 'cause we can't like see really well through it. What kind of
And
shadow
also
do we get?
There's lots of it's all in the optical.
Right.
So there's lots of dust, acid dust that
Yeah.
also obscure the view. So you're not getting a lot of stars. I don't really know the numbers. I don't do a lot of.
I'll take it. Thank you. Yeah. for-
But it drops off very quickly after a few like a few kiloparsecs, kind of time, like kind of like distance scales. It drops off pretty quickly.
Yeah, because I remember I was looking at a paper with a student maybe like 2 or 3 years ago. That's why I like these talks, because since grad school, I haven't really been. I know a lot about astronomy up to about like 5 years ago. So I mean that's what happens when you do grad school.
And the knowledge increases on the log scale.
Right.
Oh, yeah.
Yeah, we still don't actually know how many spiral arms we have. There's debate between 2, 4, some.
Yeah.
Yeah, and there's probably like minor arms. Like minor
Yeah.
features. It's not going to be like this perfect
Yes.
Spurs and stuff, yeah.
kind of grand design thing. So there's a lot of that stuff too.
Pictures on the,
Yeah, yeah, we should. Thank you so much.
Great.
Thanks,
All right,
Ilija.
enjoy the observing.
If you're ever here in town, I'll give you.
Yes, I'm sorry I couldn't have been there again.